Okay, so today I just read the introduction to Entropic Optimal Transport, the lecture notes by Marcel Nutz. And we have this the Kantorovich problem, and then we add a regularization term which is linear in epsilon, um, and basically we add a penalization term which is the entropy with respect to the um, tensor product of the two measures, which can be thought of as like the least efficient or highly inefficient um, coupling, where all of the mass from the initial measure is distributed equally onto the target measure distribution. And so we add this entropy term to essentially regularize the coupling, so that in many cases it's no longer supported on a lower dimensional set. So the support has like positive measure with respect to the tensor with respect to this tensor product of the two measures. Now, this problem can be converted into a static Schrodinger bridge problem. The static Schrodinger bridge problem was a problem studied by Schrodinger to essentially find the most likely intermediate stochastic evolution of a system given knowledge of the probability distributions at the initial and final states. So this is actually like a large deviations solution. So essentially looking for the most likely um, stochastic law which governs the evolution between initial and final states. Of course, most likely requires some underlying assumption of the stochastic law, um, which is has some thermodynamic formalism. Now, the last thing I wanted to mention is that you can perform some sort of change of variables and convert this into um, a literal Schrodinger bridge problem. Okay, so you can convert this modified um, optimal transport problem called entropically regularized optimal transport problem into a Schrodinger bridge problem by introducing a reference measure. And that reference measure is given by the e to the power minus c over epsilon, um, um, multiplied by the tensor product of the two measures. Okay, so let's just think about what this means geometrically or intuitively. So intuitively speaking, we're essentially looking at points in the support of the tensor product mu tensor nu, and we're essentially dampening the mass of points. We're introducing an exponential damping factor, e to the minus c over epsilon, and that dampening factor is going to be stronger for smaller values of epsilon. The strength of the dampening will increase, and ultimately we want to send epsilon to 0. And then, of course, the cost function between the 2 points. So we look at 2 points in the support of the tensor product, two measures, and a point. We look at a point in the support of the tensor product of mu and nu, and this point is going to have like an x and a y component, right? Um, and there's going to be a certain cost associated with this point, namely the cost of transporting x to y. And as this cost increases, the exponential dampening factor, of course, will dampen the mass of points with higher cost exponentially. So it's going to strongly dampen points with high cost. And ultimately, we search for the solution to this entropically regularized problem is in fact the coupling of mu and nu with the minimal entropy. Okay, so with respect to this reference measure. Okay, so we convert the problem into finding a coupling between mu and nu, which has minimal entropy with respect to this reference measure. So in some sense, this is intuitively a good coupling because it's close to it's entropically close to a measure, and this reference measure, and this reference measure is essentially has really high mass at points with low cost and really low mass with points with high cost, according to this exponential dampening. Okay. And last few notes that I'll say is that this Schrodinger bridge problem, in a general form, it's a minimization of the entropy functional over a convex set of measures. And typically speaking, this is, well, in the case of the entropic optimal transport, this convex set is just going to be a set of couplings. Okay. And so we perform this minimization according to the process of calculus of variations, where we first, prove the uniqueness and existence of optimizers. Uniqueness is going to come from convexity, and existence is going to come from some lower semi-continuity property of the cost functional, in this case the entropy, or the relative entropy with respect to some reference measure. And then, and then finally, we can characterize after we use this calculus of variations method. I think it's called the direct method of calculus of variations. We can then characterize the optimal solutions by a first order condition, essentially using perturbation theory. And when we perform this first order variation, as in the classical setting, we can characterize the optimizers, and this characterization can be given in the dual setting by the Schrodinger potentials, which solve something called the Schrodinger equations. And this is kind of an analogy with the Kantorovich duality in the classical optimal transport setting, in a sense that these Schrodinger potentials, they satisfy some sort of um, some sort of um, like transform property, kind of like the